Imagine a supercomputer, a machine capable of processing trillions of calculations per second, rendering complex physics simulations in real time, and holding petabytes of memory. Now imagine that this beautiful, staggering piece of hardware is forced to communicate with the outside world through a single, rusted, 30-year-old dial-up modem. Every time this supercomputer wants to output a line of code, it has to compress its massive computational power into a pathetic 300-baud trickle of data. It screeches, it struggles, it drops packets, and it takes agonizing minutes just to transmit a simple text file. This is not a hypothetical scenario from the 1980s. This is the exact architectural bottleneck of the human condition right now. You possess the most advanced neural network in the known universe inside your skull, packing roughly 86 billion neurons, firing in a synchronized symphony of chemical and electrical signals. Yet, when you want to extract a thought from that biological server farm and share it with me, you are forced to use the absolute worst input-output systems imaginable. You have to push air from your lungs, vibrate a piece of meat in your throat, and flap your tongue to create acoustic pressure waves. Or worse, you have to individually strike little plastic squares on a keyboard with your two thumbs. As an engineer who has spent decades building high-performance systems and optimizing data pipelines, I look at the human body and I see a system that is fundamentally throttled by its own legacy hardware. The internal processing speed is astronomical, but the output bandwidth is a catastrophic bottleneck. And for most of us, this bottleneck is just a frustrating reality of being human. We miscommunicate, we type too slowly, we struggle to articulate our grandest visions. But for a specific subset of the population, this bandwidth limitation is not just an inconvenience. It is a death sentence. It is a complete and total system lockdown. Consider the case of a man named Kenneth. Before January 2024, Kenneth was a high-functioning node in the global economic network. He owned a transportation business. He managed complex logistics, directed teams of employees, negotiated with clients, and maintained a rich web of communication with his wife Cheryl and his family. He was a builder, an operator, a man whose entire identity was deeply integrated with his ability to project his will into the world through speech and action. Then the system began to fail. It did not happen all at once. In systems architecture, we talk about graceful degradation versus catastrophic failure. Kenneth experienced a brutal hardware-level degradation. He was diagnosed with amyotrophic lateral sclerosis, commonly known as ALS. From an engineering perspective, ALS is a horrifyingly specific structural attack. It does not touch the central processing unit. The brain remains entirely intact, fully powered, completely aware, and perfectly capable of generating the electrical signals required for movement and speech. Instead, the disease attacks the physical cabling. It systematically destroys the motor neurons, the vital biological wires that connect the brain to the muscles. As these cables degrade, the resistance on the line increases. The signal-to-noise ratio plummets. I want you to visualize what this means on a granular, daily level. It is a Tuesday morning. Kenneth is sitting in his office, looking at his computer monitor. He has a simple directive in his mind. He wants to call a client to confirm a shipping route. His brain fires the exact sequence of neural spikes required to perform this action. The command is sent down the spinal cord. But the cables are fraying, the signal dissipates into the void. His hand remains motionless on the desk. He tries to call out to his assistant. He focuses every ounce of his willpower, generating a massive electrical surge in his motor cortex. But the muscles in his throat receive only a faint, garbled whisper of the command. The sheer physical energy required to force a signal through those dying cables is staggering. It drains the system battery in minutes. As Kenneth himself described it, you do not realize how much energy it takes to talk until you do not have that energy to waste. The coffee in his hand turns ice cold as he realizes that he is trapped. He is a perfectly functioning supercomputer slowly being sealed inside a concrete vault. The isolation is not just physical, it is existential. His wife Cheryl watched as the silence crept into their home, an invasive species choking out their daily communion. The casual back and forth, the arguments, the jokes, the simple act of saying I love you, all of it became a monumental, exhausting chore until the lines were completely severed. This is the state of biological exile. The intelligence is intact, but the port is closed. When you look at the historical attempts to solve this problem, you realize that the medical technology industry has been stuck in a tragic local maximum for decades. The legacy solutions were essentially the equivalent of putting a microphone outside a soundproof room and hoping to catch a muffled vibration. Take the system used by the brilliant physicist Stephen Hawking. For years, the world marveled at his ability to write books and deliver lectures, but the underlying mechanics of his communication interface were agonizingly primitive. Hawking utilized an infrared switch mounted on his glasses that detected the microscopic twitches of his cheek muscle. He would stare at a computer screen where a cursor systematically scanned through rows and columns of letters. When the cursor highlighted the letter he wanted, he would flex his cheek to click. One twitch for a row, another twitch for the column. It was the functional equivalent of entering a complex password using a single Morse code button. The maximum output speed he could achieve was roughly 1 or 2 words per minute. Speaking as a serial founder, when I see this kind of legacy architecture, I know the entire paradigm is broken. It is a classic single point of failure. You are relying on the very biological hardware that is actively decaying. If the cheek muscle fails, the entire communication stack collapses. You cannot build a scalable future-proof system by patching a dying component. You have to bypass the damaged infrastructure entirely. You have to build a new bridge. This is the core thesis of Elon Musk and the engineering team at Neuralink. They looked at the brain not as a mystical biological organ, but as a densely packed electrical circuit board. And their business model, their entire reason for existing, is predicated on the idea that if you can read the voltage changes on that circuit board with high enough fidelity, you can decode the operating system of human thought. But the technical landscape they had to navigate to even attempt this was incredibly hostile. The human brain is a squishy, pulsating mass of tissue suspended in corrosive salt water. It is heavily protected by a thick skull and layers of tough membranes. From a hardware integration standpoint, it is the worst possible environment to deploy sensitive electronics. The early iterations of brain-computer interfaces, the ones developed in academic labs in the early 2000s, were terrifying. They used rigid silicon spikes called the Utah array. Imagine a tiny bed of nails, completely stiff and unyielding. Surgeons would literally hammer this array into the surface of the brain. Because the brain naturally pulses with every heartbeat and shifts when you move your head, these rigid spikes would scrape against the soft tissue, causing scarring and inflammation. Within a year or two, the biological immune system would encapsulate the array in scar tissue, blinding the sensors and rendering the device useless. It was a brute force approach with an unacceptably high hardware failure rate. Neuralink realized that to solve the bandwidth problem, they first had to solve the materials science problem. They threw out the rigid silicon and engineered ultra-thin flexible polymer threads. These threads are a fraction of the width of a human hair. They are so incredibly thin and floppy that you cannot even push them into the brain using human hands. They would just bend and crumple. Therefore, to deploy their new hardware, Neuralink had to simultaneously invent a completely new deployment mechanism. They built a custom surgical robot. This was not a minor pivot. This was a massive capital expenditure. Looking at their business model canvas, they were missing the most critical component for distribution. You can have the best neural implant in the world, but if installing it requires a 12-hour open brain surgery by a team of elite neurosurgeons, your customer acquisition cost is functionally infinite. You can never scale. The surgical robot was designed to remove the human bottleneck from the installation process. It uses advanced optical coherence tomography to map the surface of the brain in real time, identifying every tiny blood vessel. The robot then takes a microscopic tungsten needle, grabs one of those flexible polymer threads, and shoots it into the cerebral cortex with sub-millimeter precision, dodging the blood vessels to avoid bleeding. It sews the threads into the brain like a hyper-advanced sewing machine, completing the entire physical integration in a fraction of the time a human surgeon would take. This is the era dividend we are currently living in. The convergence of microfabrication, advanced robotics, and heavy venture capital backing allowed Neuralink to build a full-stack solution. They did not just build the chip. They built the manufacturing line for the chip, the robotic surgeon to install the chip, and the software stack to decode the data. This vertical integration is a classic hallmark of a mature engineering-driven enterprise. It is the exact same playbook used at Tesla and SpaceX. Control the entire pipeline, from raw materials to final output. And it was this exact vertically integrated stack that Kenneth, the man locked in his own body by ALS, volunteered to test. As we prepare to dive into the exact mechanical breakdown of Kenneth's surgery and the staggering data models that followed, I need to pause for a critical request. If you are finding value in this deep dive, if you appreciate this level of raw, engineering-focused analysis instead of the usual superficial media spin, please take exactly 1.2 seconds right now to hit the like. I am not asking this for my ego. I am asking this because it is the fundamental mechanism that drives the YouTube algorithm. In the same way that Neuralink relies on precise electrical impulses to train its models, this channel relies on your engagement signals to tell the algorithm that this content is worth distributing. By hitting that button, you boost this video across the network, pushing it to other founders, engineers, and builders who need to see it. Your engagement is the greatest affirmation and support for the hundreds of hours of research that go into these deep dives. So please optimize the algorithm with me and let us get back to the breakdown. The clinical trial that Kenneth entered was officially designated as the VOICE study. It is crucial to understand that this trial represented a massive escalation in technical difficulty compared to Neuralink's previous public milestones. The earlier trials, the ones featuring patients like Noland Arbor playing chess or Mario Kart, were focused primarily on the motor cortex, specifically the areas governing hand and arm movement. When you want to move a computer cursor on a screen, the mathematical problem is relatively simple. You are looking for a two-dimensional directional vector. You are asking the brain, do you want to go up, down, left, or right, and with what velocity? It is a straightforward X and Y axis mapping. Speech is an entirely different beast. Speech is perhaps the most complex, highly orchestrated motor function the human body can perform. It requires the seamless microsecond synchronization of dozens of individual muscles across the diaphragm, the vocal cords, the throat, the tongue, the jaw, and the lips. To capture this incredibly dense data stream, the Neuralink surgical team had to adjust their targeting parameters. They moved the N1 implant away from the hand control centers. They went a few inches deeper and more lateral into the brain, specifically targeting the speech execution areas of the cortex. The N1 chip itself is a marvel of miniaturization. It is roughly the size of a large coin, hermetically sealed in a biocompatible titanium enclosure. It houses 1024 recording channels distributed across 64 individual threads. Once the robotic surgeon successfully threaded those microscopic lines into Kenneth's speech cortex, the system was live. But raw hardware integration is useless without calibration. When Kenneth woke up from the surgery, he did not immediately start broadcasting his thoughts to the world. He was discharged from the hospital the very next day, a testament to the minimally invasive nature of the robotic procedure. But the real work was just beginning in his living room. The Neuralink engineers initiated phase 1 of the data collection process. At this point, Kenneth still possessed a very small, heavily degraded amount of vocal ability. It was exhausting for him, but he could force out audible sounds. The engineers asked him to vocally speak several predefined sample sentences. This was a critical step in the machine learning pipeline. In engineering terms, they were establishing a ground truth. Every time Kenneth strained to speak a word, the 1024 electrodes in his brain were recording the exact electrical storms firing across his neurons. The system was meticulously correlating the biological intent, the neural spikes, with the physical acoustic outputs. It was building a custom dictionary mapping his brainwaves to known English words. By February, however, the relentless physics of his disease advanced. The second phase began not by choice, but by necessity. The physical deterioration of ALS reached a critical threshold, and Kenneth lost the ability to produce audible sound entirely. The cables were completely severed. In a legacy system, this would be the point of catastrophic failure. The trial would end. But Neuralink flipped the script. They transitioned the training model to decode silent mouth movements. They instructed Kenneth to try to speak the words to physically move his jaw and lips, even though no sound came out. The implant continued to watch the neurons fire. This is where the sheer computing power of the decoding algorithm became the star of the show. The system was no longer looking for whole words. It was looking for phonemes. Phonemes are the absolute smallest building blocks of language, the distinct sounds that make up words. The English language has roughly 44 unique phonemes. When Kenneth attempted to silently mouth a word, the neural network recognized the specific firing patterns for each individual phoneme in sequence and assembled them into complete sentences on the screen in. But the holy grail of brain-computer interfaces, the ultimate objective of the voice study, was phase 3. Imagined speech. This is the hardest problem in the entire field. At this stage, Kenneth was instructed to completely stop moving his facial muscles. Do not mouth the words. Do not move your tongue. Just sit completely still and think the words in your internal monologue. Imagine the sentence forming in your mind. This is where we cross the boundary from medical device to science fiction. The N1 chip, buried beneath his skull, was listening to the silent electrical echoes of his internal thoughts. It amplified that raw signal, digitized it, sent it via Bluetooth to the external decoding rig, and the computer spoke for him. The transition from phase 2 to phase 3 was not a slow, linear progression. As one of the lead researchers noted on the project logs, the progress went from 0 to 100 almost overnight. The machine learning model, having been fed enough raw data during the earlier phases, reached a tipping point. It learned the distinct neural signatures of Kenneth's internal voice. The moment this threshold was crossed, the system became highly predictive. It was no longer just matching patterns, it was anticipating his internal speech cadence. In engineering terms, this is a classic exponential curve breakthrough. You spend months grinding through flatline data, cleaning up the signal-to-noise ratio, tweaking the weights and biases of the neural net, and then suddenly the model snaps into focus. The architecture aligns, and the system performs flawlessly. But Neuralink did not stop at simply putting text on a screen, or utilizing a generic robotic text-to-speech voice. Stephen Hawking's famous robotic drawl was iconic, but it was fundamentally unnatural. It stripped him of his unique vocal identity. Neuralink took a deeply personal, highly customized approach to the output layer. They acquired historical audio recordings of Kenneth from before his ALS diagnosis. They took hours of tape from his business meetings, family videos, and phone calls, and they fed that audio into an advanced voice cloning algorithm. They trained a custom synthesizer to perfectly replicate the specific pitch, timbre, and cadence of Kenneth's original voice. The emotional payload of this engineering decision cannot be overstated. When the system was fully online and Kenneth imagined his first completely silent sentence, his wife Cheryl was sitting across the room. The speakers did not output a generic digital assistant. They output the exact acoustic signature of the man she married. When she heard the system say, "I love you," she called it the original gangster Kenneth voice. The exact voice she had heard every day for years before the disease stole it away. From a technical perspective, we are looking at a flawless end-to-end pipeline. Biological intent translated to raw electrical data, digitized into binary, decoded by a machine learning model, and output through a highly trained audio synthesizer. And the latency on this entire pipeline is dropping precipitously with every software update. The system is moving closer and closer to the speed of natural human conversation. This level of execution requires a staggering amount of capital. When I look at the financial architecture of a company attempting this, I see burn rates that would terrify a traditional Wall Street analyst. You are funding clean rooms, custom silicon foundries, robotic engineering teams, and incredibly expensive clinical trials simultaneously. You are burning hundreds of millions of dollars before you ever have a consumer product. But the underlying logic of the investment is sound, because the upside is absolute monopoly control over the next major computing platform. If you own the layer between the human mind and the digital world, the valuation of your company is practically limitless. You are no longer selling a device, you are selling the basic infrastructure of conscious interaction. When you step back and analyze this breakthrough through the founder's lens, you realize that the implications extend far beyond the medical device sector. Neuralink is not building a wheelchair for the mind. They are building a universal interface standard. In the software world, we talk about application programming interfaces, or APIs. An API allows two completely different software systems to talk to each other seamlessly. Neuralink is building the first high-bandwidth API for the human brain. Right now, the target market is individuals suffering from severe neurological degradation, like ALS or spinal cord injuries. That is the initial wedge strategy. You prove the technology in the most extreme high-necessity use cases, where the risk-reward ratio justifies the surgical intervention. But the long-term business model, the vision that justifies the massive capital burn rate of this company, is entirely focused on the mass market. If the surgical robot can be optimized to the point where receiving an implant is as safe, routine, and automated as LASIK eye surgery, the total addressable market expands to the entire human population. Why would a perfectly healthy individual want a brain chip? Because the economic incentives will eventually demand it. We are currently watching the exponential rise of artificial general intelligence. Models are becoming exponentially faster and smarter. The bandwidth gap between human output and AI input is widening every single day. If you have a team of engineers and one of them is communicating with the AI systems via a high-bandwidth neural link, instantly transferring complex concepts, raw data, and structural blueprints simply by thinking, they cannot compete on a unit economics basis. Their throughput is too low. Neuralink is positioning itself as the mandatory hardware upgrade for the human workforce in the age of artificial intelligence. We are transitioning from biological evolution, which takes millions of years to adapt to environmental changes, to engineered evolution, where we can literally patch our own biological hardware via a surgical. However, as an engineer, I am professionally obligated to point out the massive systemic risks inherent in this architecture. When you hardwire the human brain to the internet, you are introducing catastrophic new attack vectors. We are no longer just worrying about someone hacking our bank accounts or our email servers. We are talking about the potential for malicious actors to execute denial of service attacks on human motor functions, or to intercept and manipulate the raw data stream of our internal thoughts. The cybersecurity infrastructure required to secure a network of millions of neural implants does not currently exist. If there is a single point of failure in the encryption protocol of the N1 chip, the consequences would be completely unprecedented in human history. This is the dark side of hyperconnectivity. But Elon Musk is playing a massive interconnected game of multidimensional chess across all of his companies, and you have to view Neuralink as just one piece of a much larger puzzle. While Neuralink is rewriting the internal human operating system, his other ventures are radically restructuring the physical world around us. Just look at the subtle, almost overlooked hints dropped regarding Tesla's upcoming product roadmap. While everyone was captivated by the mind-reading medical breakthroughs, Musk was quietly confirming plans for a radical new Tesla family vehicle. When a Flexport executive proposed a vehicle with massive gull-wing doors for every row, completely eliminating the physical friction of climbing over seats and wrestling with child car seats, Musk responded with "This is not just a car company designing a new minivan. This is a systems engineering approach to human logistics." Tesla recognized that the legacy minivan design is fundamentally flawed. It is difficult to egress, and poorly optimized for the actual daily workflow of moving a large family. The rumored vehicle heavily implied to be built on the same angular, unpainted stainless steel platform as the Cybertruck is an attempt to completely re-architect the family hauler from first principles. If I were sitting on the board at Tesla, I would argue fiercely against the use of stainless steel for a mass-market family vehicle. The manufacturing tolerances required to stamp and assemble cold-rolled stainless steel are a nightmare. It caused massive delays and cost overruns on the Cybertruck production line. Choosing to utilize that same difficult material for a vehicle that needs to be produced cheaply and in massive volumes feels like an unforced error. It is a prime example of engineering ego superseding pragmatic business logic. However, the core concept remains sound. Reduce the friction of daily life. Optimize the physical hardware of transportation. And this philosophy of relentless optimization reaches its absolute zenith with the Optimus program. We recently saw the reveal of the Optimus Generation 3 prototype. The images shared by the engineering team showed a machine that has shed the clunky, mechanical aesthetic of its predecessors. It features a dark, sleek, heavily muscled exterior, but the most terrifying and brilliant detail was hidden in the background of the workshop photos. The central processing unit visible inside the open chest cavity of an older prototype was nearly identical to the computer used in Tesla's full self-driving vehicles. The robot is literally thinking with the exact same neural net architecture that drives the cars. The hands on the Generation 3 unit boast 22 degrees of freedom, driven by complex synthetic tendon mechanisms. This is not a research project anymore. The fact that Tesla is tearing down the assembly lines for the Model S and Model X, the foundational luxury vehicles that built the brand, to allocate factory floor space for Optimus production, tells you everything you need. They are preparing for a massive, unprecedented scaling operation. They are anticipating a run rate of 1 million humanoid robots per year. We are standing on the precipice of a total reconstruction of the global labor market. If you combine these three massive, capital-intensive projects, you see the true scope of the ambition. Neuralink is upgrading the biological processor to ensure humanity remains relevant in the cognitive space. The new transportation architecture is redesigning how we physically move through our cities. And Optimus is designed to completely decouple physical labor from human biology, creating a localized, infinite supply of productivity. We are watching the end of biological exile on a microscopic individual level, with patients like Kenneth, and we are simultaneously watching the end of biological limitations on a macroeconomic. The rules of capital, labor, and human potential are being completely rewritten in real time by a handful of engineering teams in California and Texas. The future is not going to be an extrapolation of the present. It is going to be a hard fork in the protocol of human history.